True projects. In this video, we are going to explain about the project entitled as Predicting Priority Factors for Rural E-Commerce Development using Tri-Stage Integrated Attention Residual Transformer. So before getting into the video, let me give you the brief description about the project. The title indicates a study that aims to identify the most important factors influencing rural e-commerce growth. It uses an advanced AI model called the Tri-Stage Integrated Attention Residual Transformer to analyze rural data. Overall, the title reflects a technology-driven approach to predicting and prioritizing key elements needed to enhance e-commerce development in rural areas. Coming to the abstract explains that this study focuses on identifying and prioritizing the major factors that influence the growth of e-commerce in rural areas where challenges such as poor infrastructure, unstable connectivity, and diverse socio-economic conditions make analyze extremely difficult. To overcome these limitations, the research introduced a tri-stage integrated attention residual transformer model, which is capable of capturing complex patterns and relationships within rural development data. By combining attention mechanisms, residual learning, and transformer-based modeling, the system improves prediction accuracy and provides clearer insights into which factors most significantly affect rural e-commerce expansion. Ultimately, the abstract highlights that the study's results will help policymakers, service providers, and development organizations make informed, data-driven decisions to strengthen digital commerce in rural communities. Coming to the existing system mainly uses traditional statistical methods and simple machine learning models to analyze rural e-commerce development. These approaches cannot effectively capture the complex and non-linear relationship among rural factors like infrastructure, digital literacy, and socio-economic conditions. They also struggle with noisy or incomplete data, leading to low accuracy and limited ability to identify the most influential factors. Overall, existing systems lack the depth and adaptability needed for reliable rural e-commerce analysis and planning. Coming to the proposed system or base paper work. The proposed system introduced a tri-stage integrated attenuation residual transformer, an advanced AI model designed to overcome the limitations of traditional rural e-commerce prediction methods. It combines three powerful components: multi-level attention mechanisms that focuses on the most important features, residual learning that improves information flow and prevents data loss, and transformer-based sequence modeling that captures long-range and complex relationship among rural indicators. This integrated approach allows the system to handle heterogeneous, noisy, and incomplete rural data more effectively while accurately modeling hidden patterns and interactions. As a result, the system not only improves prediction accuracy but also identifies and prioritizes the key factors influencing rural e-commerce development, providing stakeholders with deeper insights and actionable guidance. Overall, the proposed system offers high precision, robustness, and interpretability, making it a strong decision support tool for enhancing sustainable digital commerce in rural areas. Coming to the data set, the rural e-commerce dataset from Kaggle is a collection of data that represents various socio-economic, infrastructural, and digital access factors influencing e-commerce adoption in rural areas. It includes information such as population details, income levels, education and digital literacy, internet and smartphone availability, transportation facilities, and basic infrastructure conditions. The dataset also features indicates related to e-commerce readiness, including online shopping behavior, preferred payment methods, and barrier to digital adoption. Overall, it provides a comprehensive set of attributes useful for analyzing rural development patterns and predicting the factors that drive or hinder rural e-commerce growth. Coming to the novelty or extension or enhancement or improvement. The extension improves the overall system by adding feature normalization, interpretability, and a user-friendly interface. Minimax scaling is applied to the CNN plus LSTM and stacking models to improve learning efficiency, helping the stacking models achieve perfect performance with an RMSE of 0.00 and an R square of 100%. To make the predictions more understandable, explainable AI techniques like line and SHAP are used to show which feature influenced the model's decision. Finally, a Flask-based UI is developed so users can easily enter input values and get predictions from the trained models, making the system practical and accessible. Coming to the flow of the work, first we have importing the packages. All the necessary Python libraries and packages required for data handling, analysis, visualization, machine learning, deep learning, and deployment. This includes packages for data manipulation, for visualization, and for machine learning models. Importing these packages ensures that the project has access to all the tools needed for subsequent models and smooth workflow execution. Next, exploring the dataset. In this module, the ruler e-commerce dataset is loaded and explored to understand its structure, features, and underlying patterns. Basic exploratory data analysis is performed, including checking the number of rows and columns, data types, missing values, and summary statistics of features. This step provides an initial understanding of the dataset, helping to identify any anomalies, inconsistencies, or insights that guides the pre-processing and modeling steps. Next, we have pre-processing. Pre-processing is crucial for preparing the dataset for modeling. This module includes several tasks such as dynamic feature scaling to normalize the data, outer lining detection to remove or correct extreme values, and adaptive feature relevance assessment to determine the importance of each feature. Additionally, feature transformation and augmentation process are performed to create new informative attributes, and attributes refinement ensures that all features are clean, consistent, and ready for model input. Proper pre-processing improves model performance and accuracy. Next, we have data visualization. Data visualization helps in understanding the relationship between features and identifying patterns in the dataset. Techniques such as correlation matrix, scatter plots, and histograms are used to explore interactions among variables, detect multi-core linearity, and determine which features are most relevant. This model provides insights that guide feature selection and model building decision. Next, train, test, split. The dataset is divided into training and testing subsets to evaluate model performance on unseen data. Typically, a standard split like 70 is to 30 or 80 is to 20 is used. The training set is used to train models, while the testing set allows for performance evaluation and helps in identifying overfitting or underfitting issues, ensuring the models generalize well to new data. Next, building the model. In this module, multiple machine learning and deep learning models are trained using pre-processed data. Traditional models include XGB regressor, random forest, decision tree, and gradient boost, while deep learning models include EfficientNet, GaussianNet, and proposed TIART model. The module also incorporates extensions such as minimax normalization and additional models like stacking and CNN plus LSTM to enhance predictive accuracy and robustness. Hyperparameters are tuned to optimize each model's performance. Next, we have model evaluation. All trained models are evaluated using standard regression metrics such as MSE, RMSE, MAE, R square, adjusted R square, AFRS, FIE, and RAC. Next, comparing the graph. Comparison graphs are generated to visualize the relative performance of each model, making it easier to identify the best performing approach. This module ensures that model selection is based on quantitative analysis rather than assumptions. Next, we have model saving. The best performing model is saved using joblib, enabling it to be refused without retraining. Next, we have explainable AI techniques. Explainable AI techniques such as line and shape are applied to interpret the model's prediction, showing which feature most influence the output. This module improves transparency and trust in the predictive system, making it useful for stakeholders and decision makers. Coming to the front-end implementation, the front-end is developed using the Flask framework and includes a registration and login system supported by SQLite. Users can input feature values to the interface, which are then pre-processed and fed into the trained model for predictions. The predicted outcome is displayed interactively, providing a user-friendly and real-time system for rural e-commerce analysis. This module bridges the gap between the backend models and the end users. The algorithms used in the project are XGBoost regressor, random forest, decision tree, gradient boost, efficient net, GaussianNet, TIART. As an extension, we have applied the normalization along with minimax scaler, and the extension models are stacking classifier and CNN plus LSTM. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as pre-processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store user information. Now, coming to the execution of the project, firstly, copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check with any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button and user login button. Now, click on user login button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a password. We need to enter the confirmed password. Then click on sign up so that all the given details are stored in signup.db and the login HTML will be opened, where you need to access the application by username and password. Then click on sign in so that the prediction page has been displayed. In this, we have ruler e-commerce priority forecast button, graph and analysis button, notebook button and logout button. Firstly, click on ruler e-commerce priority forecast button so that the ruler e-commerce priority forecast screen will be open where you need to enter the input values and predict the output. So let us check the values. Logistic performance is of 54. Internet penetration is of 54%. Household income is 32. E-commerce awareness is 47. Trust in online transactions is 42. Gender equality index value is around 546. Skill program availability is around 456. Electricity available is of 68. Smartphone usage is of 72. Subsidy accessibility is of 56. Tech expenditure is of 49. Road connectivity is of 32. Warehouse proximity is of 21. Employment rate is 43. And literacy rate is 21. Now click on submit so that the input values are pre-processed and the output will be predicted. Here we have the predicted priority level is of 787.475954 and so on. So here we have understanding your results. We also have the recommended actions like data analysis, re-evaluation, consultation. We also have some key factors considered and we also have some next steps. And next we have predict again so that the again input form will be open where you can give your inputs and predict the outputs. And we also have back to home button and view analysis button. Now click on view analysis button so that the graphical representations of the project will be displayed. First, we have correlation matrix graph. This correlation matrix shows that all the variables have very weak or near zero correlations with each other, meaning they don't have strong linear relationship. Apart from the diagonal, the dataset shows no significant correlations or multi-collinearity between features. Next, we have MSE graph. The bar chart compares the mean squared error of various machine learning models, showing how accurately each model predicts the target variable. Lower MSE value indicates better performance. Traditional models like XGBoost, random forest, decision tree, gradient boost, and stacking have extremely low MSE scores, meaning they performed very well. In contrast, deep learning models such as EfficientNet and GaussianNet shows much higher MSE values, indicating poorer predictive accuracy on the dataset. TIA-RT performs moderately, while CNN plus LSTM shows a very low MSE similar to the tree-based models. Overall, the graph highlights that simpler models outperform complex deep learning architectures for this task. Next, we have RMSE graph. This bar chart presents the root mean squared error values for the different machine learning models, indicating how accurately each model predicts the target variable, with lower RMSE reflecting better performance. Traditional models such as XGBoost, random forest, decision tree, gradient boost, and stacking show extremely low RMSE values, demonstrating strong predictive accuracy. In contrast, deep learning models like EfficientNet and GaussianNet have very high RMSE scores, indicating poor performance on this dataset. TIA-RT performs moderately, while CNN plus LSTM achieves the lower RMSE, similar to the well-performing tree-based models. Overall, the graph highlights that simpler traditional models outperform deep neural networks for this prediction task. Next, we have MAE graph. This bar chart displays the mean absolute error for different machine learning models with lower MAE values, indicating more accurate predictions. Traditional models such as XGBoost, random forest, decision tree, gradient boost, and stacking shows extremely low MAE values, meaning they predict with high accuracy. In contrast, deep learning models like EfficientNet and GaussianNet have very high MAE scores. reflecting significantly poorer performance on this dataset. TIA-RT performs moderately with a small MAE, while CNN plus LSTM achieves a low MAE compatibility to the best performing models. Overall, the graph highlights that simpler traditional models outperform complex deep learning models in terms of prediction accuracy. Next, we have R-square score graph. The bar chart represents the R-square scores of the various machine learning models, which indicates how well each model explains the variance in the target variable. Higher scores reflect better performance. Traditional models such as XGBoost, random forest decision tree, gradient boost, and stacking all achieve high R-square value near to 1, demonstrating excellent predictive capability. CNN plus LSTM and TIA-RT also perform strongly with similarly high scores. In contrast, EfficientNet shows a negative R-square score, meaning it performs worse than a simple baseline model, while GaussianNet performs only moderately. Overall, the graph highlights that traditional machine learning models and some hybrid models outperform deeper image-based neural networks for this prediction task. Next, we have ADJ R-square score graph. This bar chart shows that adjusted R-square scores for various machine learning models, which measures how well each model explains the target variable while accounting for the number of features used. Higher values indicates better performance. Traditional models such as XGBoost, random forest, decision tree, gradient boost, and stacking achieved highest adjusted R-square score near to 1, demonstrating strong predictive accuracy even after penalizing for complexity. CNN plus LSTM and TIA-RT also perform very well with similarly high scores. In contrast, EfficientNet displays a negative adjusted R-square, indicating very poor performance, while GaussianNet shows a near zero score, meaning it explains almost none of the variance. Overall, the graph emphasizes that traditional machine learning models and hybrid approaches outperform deep image-based models for this data set. Next, we have AFRS percent graph. The bar chart illustrates the AFRS percentage for different machine learning models, where higher percentage represents better overall reliability and predictive performance. Most traditional models, including XGBoost, random forest decision tree, and gradient boost, achieve similar AFRS values around the 70% range, indicating strong and consistent performance. TIA-RT and stacking also shows comparable reliability. CNN plus LSTM stands out with the highest AFRS, reaching 100%, suggesting exceptional model stability and accuracy. In contrast, EfficientNet performs poorly with a negative AFRS value, highlighting server prediction inaccuracies, while GaussianNet demonstrates moderate performance. Overall, the graph shows that while many models perform well, CNN plus LSTM delivers the most reliable results for this task. Next, we have FIE percentage graph. The bar chart shows the FIE percentage of different machine learning models, indicating how effectively each model utilizes input features to make accurate predictions. Higher FIE value represents stronger feature usage and better interpretability. Decision tree and random forest achieve the highest FIE scores, above 90%, highlighting their strong ability to capture features, interaction, and importance. XGBoost, TIA-RT, and EfficientNet shows moderative effectiveness, while Gradient Boost and CNN plus LSTM demonstrate lower FIE values, suggesting weaker reliance on informative features. GaussianNet has the lowest FIE, indicating minimal effective feature utilization. Overall, the graph shows that tree-based models are the most effective at leveraging feature information for predictive performance. Next, we have RAC percentage graph. The bar chart compares the RAC performance of various machine learning models, showing that traditional tree-based models generally outperform deep learning approaches in this case. Decision tree and random forest achieve the highest RAC scores, indicating strong predictive ability, while XGBoost also performs moderately well, about 48%. Mid-range performance includes EfficientNet, Gradient Boost, and TIA-RT, with RAC values between roughly 30 to 45%. In contrast, GaussianNet, CNN plus LSTM and stacking model shows relatively low RAC scores, suggesting they are less effective for this particular task compared to the tree-based models. And next we have SHAP graph. The plot appears to be a dots chart showing the distribution of logistic performance values, with points scattered on both the negative and positive sides of the horizontal axis. The blue dots cluster mostly on the negative side, indicating a group of observations with lower or below baseline logistic performance, while the pink or red dots fall on the positive side, representing observations with relatively higher performance. The vertical reference line at 0 helps distinguish these two groups clearly. Overall, the chart highlights how the data spreads around a central point and suggests a noticeable separation between lower and higher logistic performance level. Next, click on Logout. So, the project successfully identifies the most influential factors driving rural e-commerce development by leveraging a tri-stage integrated attention residual transformer model. The approach enhances predictive accuracy compared to traditional machine learning and deep learning methods, demonstrating its effectiveness in capturing complex rural dynamics. Findings provide clear priority areas for policymakers and stakeholders, enabling more targeted strategies to boost rural digital growth. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.